Hello and welcome to our channel Free Education to All. So previous video, if you have observed, we have discussed about the basics of FIR filter, and now today's video, this particular topic we have divided in two different part. So in first part will be discussing, this is part 1. So here we'll be discussing these two topics: mathematical relation to find the zero locations of FIR filter, and second part, this part, so that will be a different video which will be continuation of this topic. There will be taking one numerical example and we'll try to solve it online. So let us start with this concept of zero location of FIR filter. Now we know that FIR filter can be designed with exact linear phase, and FIR filter will have the finite number of samples which are symmetric about its midpoint. So here with this going with this concept, we can say that zero location of a linear phase FIR filter are restricted to meet some symmetry conditions. For example, let us take h of n, that is equal to h of n minus 1 minus n, okay, for n ranging 0 to n minus 1. So now if we consider the system function of FIR filter, so the system function of FIR filter, we can write it in this way, that h of z, that is equal to h of e power j omega, where z equal to e power j omega. So this is basically representing the unit circle. So that is equal to summation n equal to 0 to n minus 1 h of n z to the power minus n. So if you see to this equation, this is nothing but the equation of a simple z transform. So now we can expand this in this way: summation n equal to 0 to n minus 1 h of n z to the power of minus n minus 1 z to the power of minus n z to the power of n minus 1. So this term and this term, they are reciprocal of each other. So if we multiply these two, we will get 1. So that will not make any difference to this equation. So basically we are rearranging this equation. Now since this capital N is independent of this small n, so basically this is a constant number. So we can take it out of this summation, and we can write it as z to the power minus n minus 1, that is summation n equal to 0 to n minus 1. And if we merge these two terms, what we get? Z to the power n minus 1 minus n. So here you see that this one n z h of n minus 1 minus n. So this same thing we are getting, and we are having this term also here. So this is h of n z to the power n minus 1 minus n. So now if we consider that say let m equal to n minus 1 minus n, then this will imply n is equal to n minus 1 minus m. For n equal to 0, what we get? M equal to n minus 1, and for n equal to n minus 1, what we get? M, that is equal to 0. So now we can further take it up to h of z, that is equal to z to the power minus n minus 1 summation over, now our index has changed from n to m, so m equal to 0 to n minus 1 h of n minus 1 minus m z to the power of m. So now changing this notation, that means if we change this index, from m to n again, what we get is h of z, that is equal to z to the power minus n minus 1 summation over n equal to 0 to n minus 1. Just index we have changed nothing, just for this m we have just written it to n. Even if we don't change, nothing will happen, so we can conclude from this equation itself, but for conventional notation we have changed it to m to n. So this thing we are getting z to the power of n. Now this is what we have already taken in first equation. If you go back there, first equation, what we have taken is h of n equal to this thing. Okay, so here we have taken already that h of n, that is equal to h of n minus 1 minus n. So this thing and this thing, they are same. So this implies that this equation can be further rewritten as h of z equal to z to the power minus n minus 1 summation n equal to 0 to n minus 1, and this is nothing but h of n only, because of this symmetry, because of this linear phase. What we are getting is this. So now we can write that this is z inverse to the power minus n. So now what we can say, this entire thing is nothing but z to the power of minus n minus 1 h of z inverse, So from this equation, what we can conclude that h of z equals z to the power minus n minus 1 h of z inverse. So h of z inverse and h of z, they are same, just with a delay factor. So here we can see that h of z, the zeros of h of z and the zeros of h of z inverse, they have a relation, and h of z, zeros of h of z are also the zeros of h of z inverse and some additional zeros. So this is what we can conclude from this particular equation. So let us write it in a better way. H of z, that is equal to z to the power minus n minus 1 h of z inverse. So this one is important relation, and this happens only if there is a linear phase. Now because of this, there are some symmetry properties of zeros of h of z. So let us take this symmetry property one by one. So first property, we can say if say zi is a 0 of h of z, which is a. So a is a 0 of h of z. A is a 0 of h of z. Then zi inverse, which is a inverse, which is 1 by a, is also a 0 of h of z. So this is one interesting property, symmetry property of zeros of h of z. The next property says that if zi, that is equal to e to the power j omega I, e to the power j omega I is a 0 of h of z, then zi inverse, that is equal to e to the power minus j omega I, is also a 0 of h of z. Then third property says that if zi is in the form of this ri e power j omega I. So if this is a 0 of h of z, then the conjugate of it, conjugate means zi star, this is how we write conjugate, so all of you know that. So if it is a conjugate, then the sign of j will change. So if this is a 0, then this conjugate is also a 0. And the fourth property says that if zi inverse, that is 1 by ri e to the power minus j omega I, this is a 0 of h of z, then the conjugate zi conjugate inverse is also a 0, that is 1 by zi conjugate. So which will imply that we'll have 1 by ri e to the power j omega I. So these are the 4 important symmetry properties of h of z, and we use these properties to find the 0 location of h of z. So for this I have referred these books. These are the references for further studies. You can follow these books and join me for the second part of the same topic, where we'll be solving one numerical and we'll try to find the different 0 locations of FIR filter.